And in this episode, we're going to talk about memories, digital memories to be specific. Memories are what we use to store information and then later recall it and use it for various purposes. So let's go ahead and get started. So in general, magnetic and optical type memory is where we store larger amounts of data. But it has a slower access time because it actually has to go find, that piece of the hard drive. The read write head has to go find it. So whereas a semiconductor IC can access those locations in nanoseconds, very, very, very quick. And this is typically what most people use, to take files from one place to another. If your computer or whatever instrument or equipment that you have, if it's there on a permanent basis in a spot, then you may have, some type of magnetic or optical memory nearby. Okay, so semiconductor ICs are great for, quick access, quick read write, but not on a more permanent basis typically. So everything you see here has built off of all of the concepts that we have learned from the first chapter on. Okay, so here we're talking about memory locations. Okay, we're not just talking about combinational gates anymore. We're talking about sequential systems where we have flip-flops and we can store information. So we're still referring to the memory locations by their, in this case, by their binary address. You could refer to them by their hexadecimal address as well, which is common. But anyway, here we've got 16 8-bit memory locations. So the memory address starts at 0000 and goes to 1111. And then we have 8-bit contents. Okay, so here it says that, as we know, 8 bits equals a byte. And what we store in that memory location is what's called data. Okay, and we get data from all kinds of different sensors. It could be just about anything. We store data for pictures, for video, for audio, for the state of a sensor. It could be any number of things. So if we were to implement this system that we just talked about in the previous slide, we could do it with a set of octal flip-flop IC chips. And since we have 16 memory locations, we would want to use a 4 of 16 decoder to take the 4-bit address and then choose one of the particular outputs to read or write from those locations. You'll notice in this example that all of the D inputs are tied to the same 8 bits of a data bus. Once it has the appropriate register chosen, whatever that data bus has on its inputs is going to be passed through to the Ds, and then that's going to be passed through and locked into the flip-flops for the Q outputs. So the timing of all this is very, very critical. You've got your input address bits here, and you've got your 8-bit data bus over here. And when this write goes, it gets its low to write, okay, this has to be ready and this has to be ready at the same time, or you're going to have bad data that gets passed into the memory location. And since that timing is critical, we are going to take a look at the timing diagram of this and explore it just for a second. Like it says here, a typical timing diagram might use to show timing parameters for a bus-driven device. So that's what we're talking about here. It says data and address lines are grouped together with an X to show where they're allowed to change or cross over. So again, just to revisit some terms, T sub S is the setup time and T sub P is the propagation delay. So as I said, the address and the data both have to be ready to go before this write signal gets its active low input triggered, okay? So anyway, you have the new address that's coming in, the new data, because, you're not going to always write to the same address. You're not going to have the same data. So here's the new address and the new data on the lines, okay? And this data is on the bus, right? And so now you have your write signal. So there has to be some small period of time where this is stable. The address on the lines is stable and the data on the line is stable. We talked about why setup time is important. You don't want things changing at the last minute. Sometimes you can run into a race condition when that happens, especially if you're talking about, inputs on a flip-flop or something like that. So we have to honor the setup time here. And as long as that's honored, then, before the outputs can change, and this is just a feature of the flip-flop where Q follows D, but it's not an instantaneous change that happens, right? There's a propagation delay after after the data is passed through and locked into the output. And so there's a little bit of time here. So from the first setup time, and then when this passes through its propagation delay, that's when the new data is locked in. Okay. Now, if we go back to this picture here, we've got, all of these inputs here tied to the same bus line. Okay. Now, these are all tri-state, so that, the Q here is always active, right? Because you want to keep even though you may not be writing to this right now, you still want to keep your Qs active, because you want to be able to quickly write to them. Okay. And, if Q is going to change state, you want to remember where you were, right? If you're going to save information, then you want and you're going to use a D flip-flop to do it, you want to make sure that your Qs are always active. That way you don't lose that data. Okay. So anyway, they're all connected here in a tri-state mode, and then it's only one of them that gets activated, right? So you can see here they all are connected via their clock pulse, and obviously this decodes it. It triggers one of these. The clock pulse gets triggered, and then it pulls in whatever's in on the bus and locks it into the queue. Okay, but for this one down here, just because it didn't get written on this time, you still want it to maintain what its Q values are. And so that's why all these are in a tri-state position. So if for some reason, if you had some kind of an error where more than one Q output tries to send data on on the bus, then you can have what's called bus contention. Okay. It says connecting a 1 of 16 decoder to the output ensures that the bus contention is avoided. So that's one way to prevent that from happening. So if we go back to this design, that would mean, here's all the output enable that we have here. Okay, so we're talking about connecting a decoder to that and preventing that bus contention from happening. So now let's talk about RAM. So RAM, as everyone knows, stands for random access memory. Okay, now you'll see here in yellow, it's also known as read-write memory, or RWM, but that doesn't have a clever little cliche, or mnemonic device that you can use, or acronym, whatever you want to call it. But read-write memory is the more appropriate way to describe it. But RAM is what we've always known, and so that's the industry standard. And as usual, when we talk about RAM, we're always talking about volatile memory. Okay, in other words, if you remove the power, you lose the information. So the Altera boards, the DE10, the DE1s, unless you buy a certain type of proto board, all of the Altera boards that we use are volatile. You have to download to it every time you connect it. Non-volatile would mean, it's kind of like your hard drive for your computer, where you can store information, or like an external hard drive or something like that, where you're storing information, large information, for a longer period of time. This is more for temporary storage of data to collect and hold calculations and all kinds of different things, but it's typically temporary storage, and it's volatile. So user can access any data at any location randomly. You don't have to go through an address bar like you do with read-only memory, okay, or something like that. So CD players or hard disks are examples, and you can have either static or dynamic, and we'll show what the difference is between static and dynamic. Okay, so static RAM use flip-flops as the basic storage elements, whereas dynamic use capacitors as the basic storage elements. Now, if you do have dynamic storage, because the capacitor has an exponential growth and decay for its charge and discharge, you have to add some additional refresh circuitry if you're going to have dynamic RAM. Okay, but it can be densely packed, and it's very, very low cost per bit. All right, so those are two advantages. So one example of static RAM is the 2147H. It has a total of 4,096 memory locations, which you may know at this point we abbreviate just to 4K, just to make it easier for industry. You know, my guess is that somebody found that this sells better than labeling your memory with the actual memory locations. We always just use 4K, 5K, whatever abbreviation is best. But it's actually, if you go by how many bits there are 4,096, and so each location contains 1 bit. Now, by today's standards, that's not very much memory at all, because we've got terabytes and hundreds of terabytes that even any normal person would have in their home just to store some of their their own data, their pictures and videos and things like that. But you also have to remember that's more long-term hard disk ROM storage typically, but you have to remember that's more long-term storage there, where here we're talking about RAM. Okay, but just for a comparison, even on computers, 8 gigabytes of RAM, 16 gigabytes of RAM. I'm sure there are gaming computers that are much higher than that here in 2020. But that's the kind of stuff we buy with our personal computers. So having a chip that does 4096 at this point isn't too awfully groundbreaking. But it's also a good way to explore how static RAM works. So that's why we're looking at this. To get that many unique addresses, you're going to have 12 bits. Okay, so you can see there 2 to the 12th, that's 4096 address lines. So the way that we do this is we break it up. So A0 to A5, remember there's 12 of these. So the first 6 identify the rows, and the last 6 identify the columns. So basically, this is set up, since it has rows and columns, it's basically set up like a big 64 by 64 array. So think about using the first 64 rows and 64 columns in the upper left-hand corner of an Excel spreadsheet. That's what we're talking about. And much like we call those little boxes in Excel the cells, these are called memory cells as well. So since we have the rows and columns, and we have 64 and 64, it takes 6 bits to do 64. Okay, so we actually have a 6 to 64 decoder that identifies the row, and we have a 6 of 64 decoder that identifies the column. So it's kind of like this two-prong attack. I always think of it like if you've ever played the game Bingo, where B12, I22, whatever it is. Those probably aren't even valid numbers for B and I, but whatever. You get the idea. We're identifying by the row and by the column. Okay, we're locking into that position, and the way we do that is, which row do we select? Which column do we select? We have a 6-bit that goes to 64 output decoder in both cases. So in this diagram here, you can see this is one of just a single cell of this. And you can see for the write condition, this is a 3-state buffer right here. For the data to pass through that 3-state buffer, the write enable and the chip select both have to go low at the same time for that operation to occur. So then you can also see for the read cycle here, here we're writing, we're putting new information in and storing it into the memory cell. Okay, here we're just accessing what is already on that input. So here, the write enable has to be high and the chip select has to be low. Okay, so in both cases, whether you're writing or reading, the chip select has to be low. And if you want to write, the write enable goes low. If you want to read, the write enable is high. And so that's how you can select which operation you are doing. So here's a different graphic that essentially just describes what I just discussed here. So here's the address bus that we have that we're tied into. And here we've got our cell, and so here specifies the location to be read. Remember, each memory location is a bit, and so here we've got, in this case, remember this is for the read cycle, so we're not putting anything in here. We're just reading out what's already stored. So again, for that to happen, the chip select has to be low, and the write enable has to be high. So here we look at the timing diagram for this, and we've got this period of time here, T sub AA and T sub AS. And both of those are access times, which means, the data for the output is not valid until you know, depending on how long either one of these takes. In this case, they've been set up to go for the same amount of time. But if one of them was 30 and the other one was 35, then it would still take 35. So whichever one goes longest, that's how long this access time is, okay? So you can see here, the address is already new on the bus, and the total time from here to here is called the read cycle time, okay? Now, after the access time has been passed, the data on the output is valid. It is valid, okay? Now, here it says T sub HZ, chip deselection to a high Z output. High impedance output means it's in a floating condition. Remember, that's the, what we use for the 3-state buffers, right? So if it's got a high impedance output, then obviously it's not going to be outputting a high or a low. Again, that is the float condition. And so it waits until it's asked to read again, and then it will put valid data on its output, and then it goes back to a high impedance. Okay, so that's kind of the timing sequence of what happens here. So here's the, total read cycle time. So we've got the new address, we've got the chip select, and we have surpassed the access time. Now the data is valid on the output, and then we go back to a high impedance state. So for the write cycle, again, we're connected to the address bus. Nothing has changed here. No connections have changed. But now, obviously, we're concerned about data in. And obviously, the chip select has to be low. But then we also need a low on the write enable so that we pull data in and write it to the flip-flops inside of this register, whichever register we're writing to. So here's the timing diagram for the write cycle. And as we've said before, we talked about the hold. When we talk about the setup time and the hold time for a digital signal through, some input or output, in this case, we have a hold, but it's at 0 nanoseconds, and that's typically where it is, and it's typically negligible. But just showing, a typical access here. So here's the entire write cycle, and here's the address on the address bus. The chip select had to have been low. And remember, we're not showing it on this diagram here, but we're assuming here that write enable is also low, okay? So, anyway, there's the chip select low, and then, there's a period of time where the data, it says it doesn't care. Data in is now valid. I don't like the way this is worded because it kind of looks like data invalid, but it's data in is valid, okay? And that's that T sub DW, data valid to end of write. So this is where it's good. And again, these type of things will be set up in the specifications so you know how long it takes at each step of this process. So that's just looking at the operation of one of these. Now, obviously, we can put multiple of these together and have a bigger memory, and then, we have more memory locations we can read and write from. So we can expand this, to, I'm not sure how far you would want to go with this, because it would start to become pretty pricey, and you'll see here in a second why we might choose to use dynamic RAM if we're going to be storing, larger pieces of data, because this is a very expensive way to do it. So I guess it's a good point to start talking about dynamic RAM. And so, the first thing is in spite of the extra support circuitry that you need, and it's more difficult to use, it's less expensive per bit, and you can get higher density, which means you have a smaller size per bit, which obviously with modern technology is something that we want, because we want to make things as small as possible in some cases. So as we discussed, static RAM uses flip-flops as the main storage medium, and here we are using charge on a capacitor. The other thing is, because of the nature of the capacitor, and you cannot immediately change the voltage on it, it has to build up charge, and then it takes time to release the charge. So it actually takes a little bit longer to make those changes. The static RAM example that we looked at uses MOSFETs, and it's much easier to switch those from an on or off position than it is to charge. Well, I should say it's quicker to change the transistor, turn it on or off like a switch, versus the capacitor, which has to charge and discharge. Okay, so for instance, if you wanted to write a 1 to the storage capacitor that we're using here, right now, and until we get this pulse on the gate, this is isolated from everything, okay, until this shorts out with a pulse. So once that happens, the D1 will have VCC on it, or a high, and in which case sometimes it's 5 volts, could be 3.3 volts, but whatever it is, it's a high. Okay, when this right pulse hits the gate, it shorts the drain to the source, and we get current flow, and it will charge the capacitor. Okay, and that voltage, whatever that voltage is here, gets put on this capacitor. Okay, so the DRAM circuitry has to provide that right pulse when this is ready. Okay, now if you're going to read from it, something else happens, right? It's now redirected to where when the read pulse hits here, instead of having VCC, we've redirected it now to where it's going to short again. This pulse is going to turn the transistor on. It's going to create a short between the drain and the source, and it'll put this positive VCC voltage right on D out. So when this happens, obviously, if you want to keep the storage on here, you're going to have to constantly refresh this. Okay, so we have to have some circuitry that will enable this to happen because the capacitor does not hold its charge forever. So you can see here, this is an example. If we on that capacitor, this is the one we're talking about here, the storage capacitor here. So here we put a 1 on it, and it depends on the family, the DRAM family, but this is the refresh period. Okay, so it has to constantly get new voltage reapplied to it, okay, so it can keep its high. Remember, it's still a high even though we have this sort of a seesaw wavy looking line. As long as it's above the threshold for what a high is for that family of chips, then we're okay. But this is why it's a little bit more involved if you use DRAM as opposed to static RAM, because you have to constantly refresh your high. So this refresh cycle timing says here usually every 2 milliseconds or less. However, some of the newer technology can be up to 64 milliseconds or even more. Okay, so it just depends. You have to look at the specification sheet. This isn't a good, I wouldn't say this is a good blanket statement for all DRAM families and chips. There are a few ways that we can refresh these cells. One way is to do a read cycle. That will do it, if you're accessing it. A write cycle, obviously, will refresh it. So you could just keep writing over and over to it, keep writing a 1. But really the best way to do it is with this, what we call a row address strobe only cycle, okay? And remember, this needs to happen every 2 milliseconds or less, up to 64 milliseconds. That needs to happen over and over and over to keep that data preserved. If the application that you're in is constantly reading and writing to every single memory location all the time, then you don't have to use the row address strobe. But you typically, in most cases, are not doing that. And so here's what we would do for that procedure. So as we said here, we only want the row address strobe, which is a active low input. We want to make sure that the column address strobe is high in this case. So then the A0 through A6 part of the address is set up with row address of 0, okay, to start at the very, very beginning. Then the row address strobe is pulsed low. We increment the front end again by 1. And we go to that memory location and pulse low. And then we go to the next memory location and we pulse low. And this happens over and over and over. In this case, we're talking about one with 128 rows. So it says repeat 3 and 4 until all 128 rows have been accessed. So again, you have to have something in place that's constantly refreshing this circuitry. And again, I'll just reiterate, if you're not going to read and write often enough to every single memory location with the other things that you're doing, then you want to use these row address strobe procedures. Okay. So here's an example of a cycle for the timing on a DRAM. So here, the first thing that happens, we have our addresses on the address bus, remember. So the first thing that happens is we load the row address with this signal, okay? And then right after that, it's kind of like a 1, 2, we load the column address strobe. Okay, and that gets loaded in, and then after a certain period, once the access time for the row address has been completed, and also for the column access, then we have valid data that can be sent out. So if we're talking about the write cycle, okay, same thing. We have to have a row address strobe hit first. That'll load in from the row part of the address, then the column part of the address with the column address strobe, and then we have valid data in. We have to have a setup time and we have to have a hold time again. Okay, now the hold time just depends on the family, what that is. We saw in some cases it could be 0 seconds. So it just depends. You have to look and see what this is. But anyway, it will accept this data in as long as it was stable for this setup time, and then it holds stable in this hold time after we have had our row address and our column address strobes. So some of the newer ICs have taken this stuff into account, and they've come up with a way to simplify using the DRAM. Takes a lot of work to constantly demultiplex the address, and then also for the refresh on all the capacitors. And if you want bigger memory, obviously you would solder more and more of these together on the same board. Okay, and that's how modern RAMs are actually built. And it's so easy these days that anybody, even without any engineering experience, can add more RAM or change more RAM, because there's a special socket in your computer that does it for you. So this dynamic RAM controller makes everything so much easier, because now you only have to worry about really 3 of these lines here, where you have the refresh enable. You just send the 1 pulse, and then this takes care of refreshing everything after that. Okay, you have the row enable, and then you have a count here on this and a 0. So you're still connected to the address bar, and then that gets passed through. Okay, we still have those connected to the inputs of all of these. The 3242 is a common one. Here you see the 2118, which we kind of referred to, even though I didn't name it. That's really what we were talking about in these previous dynamic RAM episodes here, where we're talking about 128 rows access. That's from the 2118. Okay, so the 3242 is a common one of these controllers. Now we're going to talk about what we call ROM, or read-only memories. So here's where we want to store data on a more permanent basis, and since we're going to do that, we may not always be connected to power, so this needs to be non-volatile memory. So we want it to be retained even when power is removed from the circuitry. So, one of these is erasable, programmable read-only memory. There's electrically erasable, programmable read-only memory, which is EEPROM. And then there's just PROM, programmable read-only memory. Okay, so it depends on what you're doing. This is not the type of memory where you want to write and rewrite over large blocks of information. This is, kind of more permanent storage, so you don't want it to be changing very often. So, operating systems. Now, I realize that operating systems have updates all the time, but most of the code is retained for years and years and years in the same spot. Table lookups, language compilers, even if you have a like a microprocessor application, if you're going to embed some data on there, you want it to be retained, and you want it to be non-volatile. Okay, so one way to create this, or have this ROM memory, is to create a mask ROM. So you can have somebody design this for you if it's a big enough circuit that you want to design and it's worth their time. I think the threshold is like 1,000 chips or something like that. So they have a one-time fee to design the unique mask if you know exactly what kind of memory you want that's not going to change. So I think this is, the one-time fee, we're probably talking a couple of $1,000. But once you have that, then you can, once you have that design, every IC that you make after that is very, very inexpensive. And so this is what a lot of companies will do. So think about the memory that your computer keyboard uses. Okay, your computer keyboard never ever changes. When you type a K, that has a certain value to it, ASCII value to it. When you have a capital K, that's a certain value. All the characters that get displayed on the screen, they don't change. We don't change the alphabet. We don't change our punctuation. We don't change the new numbers that we use. So in those situations, if you are a keyboard manufacturer, then you're going to use some type of a mask ROM where you have a very specific, detailed purpose for the memory that's not going to change, and it's gonna exist and be the same for years and years and years. You know, you pay the one-time fee to get the memory required to do that decoding or whatever, and then you can manufacture the subsequent ones very, very cheaply. However, obviously you're going to want to test through the mask, you know, if this happens, to make sure, you know, before you make a million of something. I don't know if you would make a million of them, but however many you make, you would want to test through it and make sure it's exactly what you need before you start that process. So if you don't like that approach and you don't want to have to put out that money for that initial one-time fee, you can use what's called a fusible link programmable read-only memory. Okay, so in this case, every single bit, every single memory cell has a fusible link. Okay, and whatever is on there, whether it's a high or a low, okay, this is burned permanently as an open. You know, you can see here, this says the permanently burnt fuse link creates an open in the source circuit. An intact fuse maintains source connection to ground. Okay, so whether you're storing a high or a low, if you're going to store a high, you burn out the fusible link and you leave the other ones alone. Okay, and so that'll give you permanent ones and zeros in this programmable read-only memory. So again, these are very specific situations where the contents of the memory location are not going to change over time, and you are not going to need them to change over time. So two other popular types of read-only memories are EEPROM and EEPROM. And in each case here, we're allowed to erase what we had. Remember, like with the fusible link, once it's burned, it's burned. All right, so here, with the EEPROM, we can change the memory contents. All right, so what it has here is it actually has a little window, and when you expose it to ultraviolet light, it will actually erase everything that's internal to the chip. But it's very, very slow. This is not something, you know, we're used to USB speeds and that type of access and that type of transfer. Remember, this is not that type of storage. This is a permanent storage. So you can update what's on here, but you have to erase it with an ultraviolet light. Electrically erasable, EEPROM, is non-volatile also, but it can be erased while the circuit is powered up. Okay, so, you know, here you've got to pull it out and you have to expose it to the ultraviolet light for a certain period of time, and it will erase everything, and then you can override it. Okay, whereas a EEPROM, you can erase it while it's in the circuit, you know, with a signal. Now here's the thing, these are still not built to be written over and over. This is what is used inside of PLCs, programmable logic controllers, to store not the program that keeps getting downloaded from the user, because that can happen thousands and thousands of times. This is the firmware that's inside the controller. Okay, so, you know, if you have a certain controller, you want it to use a certain version of the software, and so, you know, you may change it once a year, and that's it. Okay, in other words, so if this is built to withstand 1,000 overwrites, then, you know, presumably you could use it for 1,000 years. Obviously, that's probably not going to happen, but that's the idea, is that they're not meant to be written over thousands and thousands of times. They're meant to hold things on a more permanent basis. So these days, what we use more of is what's called flash memory. Much, much faster access times. You can erase huge blocks very, very quickly. You know, it's not like the EEPROM or the EEPROM. And you find this stuff in digital cameras, in your smartphones, all of your personal devices that you carry around. So, for example, most operating systems, most computers these days store their operating system firmware on flash memory. Okay, so this is very, very common. Another place is when a printer stores fonts, right? The fonts aren't going to change over time. You know, Times New Roman is Times New Roman today, and it's Times New Roman 10 years from now. So that font is not going to change. So there's no reason to have, you know, just regular storage. You can put that on a flash memory and store it on a more permanent basis. So here's an example of a 2716. That's just a type of EEPROM. But anyway, you can see here, we've got our address bus again. and we've got our data bus. Here's where we're going to be outputting to. This is a 2K by 8, so it's a 16K storage memory, and it's oriented with 2K by 8. Okay. So as you can see here, the address gets put on the bus, and here's where the address is valid, right? And you can see all of the little timing specifications down at the bottom of this. So for the read cycle, we have to have the chip enable go low, and we also have to have the output enable go low. So at rest, the output is in a high impedance or a floating condition, right? Once these two things have happened, once that timing delay has passed, the data is then valid on the output, right? At the same time that the address is valid. So if you've got more than one of these IC chips in your circuit, then you're going to have to do some more decoding, right? So we keep talking about decoding, but you know, think about it. It's really the only way that we can communicate between these different chips, because we can't put the number 15 on a line. We can only put ones and zeros. So we're constantly taking a value and converting it into a single output through all of this decoding. Okay, so here we go. So if you've got more than one here, you can see that the enable signal is coming from the microprocessor, and we have the address on the address bus here, and so that's going to get passed on, and we're only going to turn on one of these. So we've determined that, you know, this address is I assume this is 000 here. Yes, it is. And so this is the next memory address. This is the next memory address, the next one, and so depending on which address is on the address bus, this will decode and turn on the appropriate memory that we're supposed to be accessing at a particular time. So again, just to reiterate, the microprocessor is the one that sends the enable signal, but first, before it does that, it has to put the address on the address bus, and then it releases a low signal to pull that address through this decoder chip. So again, we're using decoders all the time. We use them, in this case, to decode which chip we're going to use. We can decode which memory location we're writing to. We use decoders all the time. So here's a good example of where this would come in handy. So we know from our previous discussion on analog to digital converters that a thermistor is a nonlinear device. So every step up, you know, that you're going to count in binary, or every count in decimal for that matter, is not going to be linear, and it's not going to be proportional for each step. So that's a problem. So as we know, the thermistor is going to change as the temperature changes. And again, it's nonlinear, but as that resistance changes, it's going to change the voltage that drops across it in this small little voltage divider here. So the analog voltage into this analog to digital converter is going to change based on what the temperature is. So then we take that analog voltage in, convert it to an 8-bit digital string. That can be passed on to the EEPROM or the PROM here. Now here's the thing, for this to work, we would have to have some type of a lookup table in here, because we're using these 1, 2, 3, 4. We're using these 4 bits right here as a BCD number. So we would have to have some type of lookup table where we take the inputs on A0 through A7. We would have to have a lookup table inside of that PROM and take it and take that binary and make 2 BCD string, 4-bit BCD strings out of them. So once that happens and we've determined what the 2 4-bit BCD strings are, as you know from there, that's a standard operation. We go to some sort of a BCD to 7-segment display. However, this has to be an LCD decoder, because that's what we have here in this picture. We could send them to LEDs, but in this case, it's sending them to LCDs, which is liquid crystal display. And really the only difference is the LCD consumes a lot less energy than the LED. The trade-off, though, is you have to have some sort of a square wave oscillator to operate the backplane. So that's not a decoder that we have talked about. We typically talk about the 7447 or the 7448 because those drive LEDs, right? But in this case, in this example, we're using LCDs, and so we would have to have a different type of decoder to go from BCD to the 7-segment display on the LCD. So if we go into our time machine and go back to the 1980s, let's say, most of the PCs operated with a 5 1/4 floppy disk. Okay, very, very, very low storage. And then sometime in the 90s, I can't remember what year exactly, but we upgraded to a 3.5-inch floppy disk that stored 1.44 megabytes. Okay, and so this was revolutionary at the time. So internally on these, they had it was a circular magnetic, some type of material that could be magnetized, right? And it was in a circular shape, and it spun at a certain speed. And that's what we used to use to store like Word documents or Excel files, things like that. Most of we didn't have a lot of digital pictures and videos and things. And so those were very, very common to store documents, which is what we used to store. All right. So this is really the precursor to what we know now as the USB drive or the flash drive. But one of the biggest problems with those old storage drives, if you pulled the metal sleeve open that protected the medium inside of there, you could actually erase it if you got it close to a magnet. So these days, sort of the remnants of that, the larger storage that gets put on what we call platters in the hard disk drive. Since those are more permanent, since they typically stay in the same place, they stay in their same housing, they don't travel from one place to another. And since everything is very, very tightly defined per bit, you can cram more of them in together. And as I said before, we are now to the point where we are storing terabytes of information on these devices. Optical memory is a little bit newer, and we're talking about like the 90s, wide scale use in the 90s and on, and they're still used today. There are still folks who use DVD players, Blu-ray players, CD players. Some people have, when CDs first became available to replace some of these old floppy disks, everyone started doing these large, what would you say, permanent storage or long-term storage or backup files on these larger CDs and DVDs. The problem is we got to the point where we started having these bigger and bigger external hard drives that became very, very cost effective to do that type of stuff for us. So a lot of people still haven't upgraded though to the newer external hard drive and still have a lot of their old storage on these DVDs and CDs. So folks still use them, and some people are resisting the streaming effect that Netflix and other companies have had on media. And so now you don't even buy your CD, your audio CD or your DVD. A lot of people have just forgone that altogether, and they buy a digital copy of it that they can either just stream from the servers where they get the service, or you can store it locally on your hard drive. Okay. But that is, it's a little bit different because this is magnetic, and so you've got polarity. Whereas optical, they use these pits and pits and lands to be read by a laser system. And again, because this is defined, you can really, really cram these in close together. So you can have a high density DVD that has like 8 gigabytes of storage on one single, piece of plastic with a storage medium inside of it. So in both cases, these require typically either the platter to be spinned, or the magnetic ones use, the older ones anyway, will use the smaller medium, but it still had to be spun around and read by some type of a read-write head. Same thing with optical CDs, DVDs, they need to be spun, and then a read-write head can then go access or write that information. So as I said, we have a magnetizable medium in the floppy disk, and now this one is specifically talking about the 3.5-inch, but I referenced the 5 1/4 as well. Because it was the predecessor. But, the big thing here is these were removable. You could take it, you work on something at work and then start to take it home. And so, here's some of the transfer rates of that technology. 45 kilobytes per second. Here in 2020, that's probably quite unacceptable for the amount of data and information that we trade in, nanoseconds. So you can see in comparison to the hard disk, we have very, very closely packed bits together because it stays in the same place. It's not removable. It's a very rigid platform. It's sealed. and it's also two-sided. So you can see here the difference. It says these have concentric circles that are called tracks, and there's 20,000 tracks per inch. Okay, so that's a lot of storage capacity in a small space there. And it says that you can have 300 kilobits per inch on each track, and you have transfer rates. Now you've changed the game considerably. Now you can go up to 30 megabytes per second. So again, that is megabytes per second. So this is a good explanation of what you see on the underside of a CD. Okay, so again, it's not as fast as the hard disk, but it is removable, and so that's nice, right? And so, this also was a much, much bigger, we really didn't talk about the zip drive, which was sort of the in-between, but it still played off those same old principles. And I think that the highest, at least the one that I had back then, and we're talking around 2000, that was a 256 megabyte zip disk. And I thought that I would never need another storage device ever again. But then the CD, the read-write CD became more popular, and people started getting read-write drives. And now, now the zip drive didn't last very long because the CD pretty much took over. Much, much cheaper, to buy a CD versus a zip drive. And so this is what became popular. And so the pits are ones and the lands are zeros. And so you just have a series of ones and zeros that go concentric circles around around the circle. Okay, so we kind of already went over this, but you've heard of the different terms. So a CD, says land reflects light, pit does not. And so then you can get into the CDR. It says photosensitive dye on the reflective gold layer. Laser superheats spot and it will not reflect. Cannot be erased or rewritten. So this is what you were buying in the 90s and the 2000s. Same thing with the DVD-R, okay? Anytime you saw the R, it just is read-only. So essentially, they locked it in place to make sure that you can't overwrite it. And for that matter, they also put some other stuff in there so that you can't copy it. But obviously, people found a way around that technology. But, most people, when they bought CDs back then, to make a copy of it, they would, put it onto a cassette tape. If you remember what those are, that's magnetic storage too. So the read-write, again, as I said, became more popular, and it has to know whether it's reading or writing, but you can do both on these. And so you could store data, you could rewrite it, you could store data and rewrite it. And then the DVD standard came along, but 4.7 gig, I forget what it is, 8 point. Whatever it is, it's around 8 gig is another size, and then you can go all the way up to 16 gig. So it just depends. There's dual layer. The Blu-ray discs sort of play off of that, where you can put much more data onto the same, essentially the same size medium, right? So the difference in thickness of a DVD or a CD versus a Blu-ray is not detectable typically by humans. So, we're able to cram more and more information in the same space. Okay, well, that ends our discussion on memories. Thanks for watching.